Okay, so today I'm going to finish up deriving these equations so you can see where everything came from, okay? So the first big equation is this, f equals big M2 over d squared, okay? So all that does is that the only thing that you have to do this calculation is the gravitational force between the objects is going to be dependent upon three things. The two masses and how far apart they are, okay? That's it. So what this means cosmologically is that you are obviously gravitationally attracted to this big rock that we're on. You are also gravitationally attracted to the sun, to the moon, to Jupiter, to Saturn, to the Andromeda galaxy, to the most distant star in the most distant galaxy on the other side of the universe. So you are gravitationally attracted to everything else that exists in the universe. But because it's d squared, as that distance gets greater and greater and greater, that force functionally basically goes to zero. So even like on a full moon, okay, when the full moon is directly overhead and you're standing on the earth, okay, and you have that full moon directly over here, it's a little bit of a tug of war because that moon is actually attracting you towards itself and the earth is obviously pulling you this way. Now, technically on a full moon, you're going to weigh a smidgen less because that moon is going to be pulling you in this direction. Not enough to make any difference, okay? But technically you're going to weigh a little bit less. But what is important is this is why we have tides. Because the the oceans are being pulled towards the moon. So if you've ever lived near the ocean, you always keep track of like the tidal schedule. Because of the fact that that tide, because as the earth is spinning, you have different parts of the water on the ocean that are pulled towards the moon. So as that's happening, that's what's creating tides. And one of the things that they think about as far as us being able to be here and have this discussion, the moon gives us two really big advantages. It stabilizes our orbit, and the other big thing is that what the moon did is that because we had tides, that on the coastal areas, that allowed a continuous exchange of water. And they think that might have aided that evolutionary process because that water wasn't just stagnant along the edges of the oceans. It was always being continuously exchanged because of the tides. So that's one of the big things that really helped us out as far as us being able to be here and have this discussion. Okay, the biggest thing is it stabilizes our spin. Okay, now, out of that, what we came up with yesterday, we also came up with little g equals big G mass of the earth over r squared. So what this gives you is the gravitational acceleration standing on the earth, the moon, Jupiter, whatever that is, and notice that this is also dependent upon r squared. So one of the things that you're going to see again and again and again is that this radius is always from the center mass out to that point. This isn't like a surface to surface distance. So when you're talking about a planet, you're talking about how far it is from the center of that planet out to that edge. So what this means is that little g on the earth is not a constant value. It actually changes depending upon where you are. Like if you're on the top of Mount Everest, it's going to be a little bit smaller. If you're standing by the ocean, g is going to be a little bit bigger. Now, is it really going to make that much difference? No, but here's what's important. This is why little g isn't a universal constant like big G is. So big G is a constant no matter where you go. Earth, the moon, Saturn, doesn't make any difference. Big G is going to be the same. Little g changes and is dependent upon how far you are from the center of the moon, or the center of the moon, or the center of the earth, wherever that's going to be. Okay. Now, let's come up with, we have two big equations that we need to derive. And they're both based upon the same idea. So here's the earth, okay? And here's the satellite, okay? And so we've got the satellite, I don't know, Caden, okay? So here's the satellite Caden, all right? And the satellite Caden is in orbit around the Earth, okay? Now, the satellite doesn't want to travel in a circle. The satellite wants to travel in a straight line because of Newton's first law of motion. So, because of the fact that it's traveling in a circle, that means there has to be some centripetal force acting on it. Now, here's the big idea, is that centripetal force is going to equal the gravitational force between the Earth and the satellite. That's the only thing. Okay, when we launch a satellite, it isn't like we tie a rope to it and we get it swinging around like this isn't how we launch satellites. We don't tie a rope to it and anchor it to the Earth and have it go around the Earth on the end of a string. Okay, not very practical, but it could work. So, the whole idea being is that this is going to be important. The centripetal force is going to equal the gravitational force. So, to calculate the gravitational force, we're going to start with the right side of this equation. To calculate that gravitational force, we need three things. We need big G, the mass of the satellite Caden, the mass of the Earth, and how far we are from the center of the Earth going out. Okay? That isn't from the surface of the Earth. It's from the center of the Earth out to that point. If we know these three things, we can calculate the gravitational attraction between the satellite Caden, the mass of the Earth, and if we know how far it is, we can calculate that value of the force. Now, that's going to equal the centripetal force. So the first centripetal force we're going to deal with is the one that involves velocity. So that would be the mass of Caden times velocity squared divided by r. Okay? So here's the big thing. And Caden, no offense, okay, this is going to happen to everybody, just like it happened to Joel yesterday. Okay? Notice that I've got Caden on both sides of the equation. So Caden's going to drop out of this equation. Okay? It's going to go away. So what I want to do is I want to solve this equation for velocity, because Caden's out at this point. Okay? And it isn't just Caden. Like I said, it's going to happen to everybody. So if I multiply by r, so I get big G, mass, nope, screwed that up. I wrote G too many times. I got big G times the mass of the Earth times r, then divided by r squared, and then that's going to cancel that out, and that's v squared, so I get v equals big G, mass of the Earth, divided by r. Okay? So let's talk about this. So, assuming that you're always orbiting the Earth, this number up here won't always change. So if you're really a model of efficiency, okay, if you were really a model of efficiency, if you wanted to store another number in your calculator, you could take big G times the mass of the Earth, get that answer, and then store that. Okay? You'd have to be really kind of an efficiency, I don't know, aficionado, or really, really hardcore into it, instead of just storing these numbers and just saying it's just two recall numbers. But you can store that if you wanted to, because what you'll see a lot of times is that we do multiply big G times the mass of the Earth. But here's the bigger idea. We're going to divide by this radius. So here's what I want you to look at. As the radius gets bigger and bigger and bigger, the velocity is going to become smaller and smaller and smaller, because you're dividing by a bigger and bigger number. So as you boost a satellite into a higher and higher and higher orbit, the orbital velocity becomes smaller and smaller and smaller. Okay. So let's say that, I want to pull up a problem here. Okay. So let's say that we have this problem, we want to work this. So this is what you're going to see in your homework problems. So we got a satellite that's 122 kilometers above the surface of the Earth. I want to calculate 4 different things, okay? I want to calculate how fast it's going. We're going to do that first. We'll get to the other 3 in just a second, okay? But let's just talk about the velocity first. So we have this equation, right? We'll get to the other ones later. So we have V equals the square root of big G, mass of the Earth over R. Now, you'll notice that I didn't give you the mass of the satellite. I didn't give you the mass of the satellite because it doesn't matter. You can't plug the mass of the satellite into that equation if you tried. Just like I didn't tell you, oh, it has 2 really big solar array panels on it. I didn't tell you that either because it doesn't matter. Okay? So the only thing that's going to determine that velocity is how far above the Earth it is, the mass of the Earth, and that's it. Those are the only 2 things. So what we're going to do, and I'm just going to leave this as big G, mass of the Earth. Now, here's what you're going to do wrong. Okay? You mark my words. You're going to see 122 kilometers, and you're going to try and put 122 kilometers in here, which is going to be a train wreck for any number of reasons. First off, this big G is newtons meters squared over kilograms squared, which means if you're going to make this thing work out, that radius has to be in meters. So you can't even put that as 122. So what we're saying is that this distance, we'll highlight that. Oh, great, it won't let me write on that. So that distance from the satellite to the surface of the Earth, if you multiply by 1,000, is 122,000 meters. Okay? That's the distance to the Earth. But that's to the surface. So what are you going to have to do with that number then? Oh, I hate this. It sucks to interact with you guys. What are you going to have to do? What are you going to have to add to that 122,000?
The distance to the center of the Earth.
Fantastic, because it has to be a center-to-center distance. So I'm going to take 122,000 and add that to 6.3713 times 10 to the 6th meters. So somebody take 122,000, and I don't know what this answer is. So take 122,000 and add that to 6.3713 times 10 to the 6th meters. And let me know what you get. Come on, there's 14 of you. Surely somebody has a calculator that can do this. It's exactly 6.49?
Oh, no, it's 6493700. I would actually figure out what the number is.
64937? Okay, so here's the deal. When you're doing this subcalculation, don't round this number, okay? Don't round this number. Keep this number and then round when you get to the end, okay? Don't round this, okay? Listen to me. Do not round these numbers. You round when you get to the end, okay? Keep all of the digits, if you're converting into seconds, whatever that is, keep all your digits and then round when you get to the end. Now, before you do any calculations at all, okay, I want to look at this on an order of magnitude, okay? So I've got G is 10 to the negative 11th, the mass of the Earth is 10 to the 24th, and this is going to be 10 to the 6th, okay? So I got 10 to the 24th times 10 to the negative 11th, that gets me 10 to the 13th. I take 10 to the 13th, divide that by 10 to the 6th, I get 10 to the 7th. But then I'm taking the square root of that, so that gets me around 10 to the 3rd. So what you'll see is that objects that orbit in a near-Earth orbit, okay, around the Earth, and you also see this, that's true around the Moon, is that these order of exponents for your velocity should be 10 to the third. If you ever get a velocity like 10 to the 7th, 10 to the 8th, which is like then you're approaching the speed of light, you have done something horribly, horribly wrong. Okay? So, it's a simple check. When you calculate a velocity in a near-Earth orbit, or with our Moon, you should get an order of exponent of 10 to the third. Okay? Just a ballpark, 10 to the third. Okay? Now, somebody actually crunched this number. Take big G times the mass of the Earth divided by 6.4937 times 10 to the 6th, and then don't forget to take the square root of that. So what'd you get? And by the way, this is one of those, when I was in school, when I was in high school, my physics teacher wouldn't allow us to use calculators on tests. So we had to be able to do these calculations by hand. It sucked. Okay, anyway. What'd you get?
7,867, and then it's a double zero after it.
So 3 significant digits, okay? So we got 7,870 meters per second, okay? Or 7.87 e to the third, okay? And that's kind of what we said was going to happen, right? So we said it was going to be something times 10 to the third. Okay, hey, we're good, right? Now, and again, play the what if game. Is that if I boost this thing into a higher orbit, the only thing that's going to change is I'm going to be dividing by a bigger radius, so that's going to make that velocity become even smaller. Okay, now we're going to get back to the other things I want to do. Now we've got to derive another equation. So, we're going to go back to the satellite Caden, okay? As Caden's orbiting around the Earth. And we're going to look at the centripetal force still equaling the gravitational force, which is still going to be big G, mass of Caden, times the mass of the satellite divided by r squared. Now, the other way to calculate centripetal force is the one that involves 4 pi squared r over t squared. So I'm going to put mass of Caden, 4 pi squared r over t squared. Now, again, here's what's going to happen. Okay, no offense, you're going to drop out of this equation. Okay, so you're going to go away. So, what I'm going to do at this point, I'm going to cross multiply. I'm going to take 4 pi squared r times r squared, and then I'm going to have big G, mass of the Earth, times t squared. That's going to be Earth. So I'm going to have 4 pi squared, this is the pirate's favorite equation, because it's 4 pi squared r cubed equals big G, mass of the Earth, times t squared. Now, this is what is like the Swiss Army knife of all equations relating to planetary motion. Because this has the most things in it. It has radius, it has mass, it has period. Okay? So what we observe, and you'll see this later on, is that, like for example, you want to talk about Jupiter. Well, it's tough to accurately measure like necessarily the velocity of a moon of Jupiter. But what we can figure out is like the orbital period of a moon of Jupiter. And we can get a pretty good idea of what that radius is based upon a scale looking through a telescope. So what we can do then is we can solve for like the mass of Jupiter. And this is one of the things that you're going to be able to do. So this equation, and if I were you all, as you're preparing for this test on Thursday, be able to come up with this equation. Okay, it's 4 pi squared r cubed big G mass of the Earth t squared. Okay, Ideally, you'd be able to derive it. If you just want to understand it, that's fine. But this is a Swiss Army knife, because you can do so many things with it. So typically what you'll do, what normally happens, is that you either solve this for period, which is what we're going to do, or you solve it for mass. It's rare that you solve it for radius, but you've got to be able to do that. So one of your problems on your assignment is that you want to find the orbital radius of a geosynchronous satellite, where you know the period, the mass of the Earth, 4 pi squared, and you'd want to find the radius. So you've got to be able to take this equation and solve that for any variable of radius, mass, or period. Okay, so if you go back to where we were, okay? Now, remember these numbers. Now, at this point, we want to calculate the period of the satellite, okay? So, to calculate the period of that satellite, we're going to go, we said that we had 4 pi squared r cubed equals big G mass of the Earth times t squared. So, we're going to solve this for t. So, we're going to have 4 pi squared r cubed divided by big G times the mass of the Earth. And then we're going to take the square root of all of that. Now, a lot of times how you see this equation written is that the square root of 4 pi squared is 2 pi. So a lot of times when you see this equation, you'll see it written as 2 pi times r cubed over big G mass of the Earth. Okay? So if you see it like this, all they did is they took out the square root of 4 pi squared. Okay? That's all they did. It isn't anything radical. It's the exact same equation. Now, again, if you're really into efficiency, assuming that this satellite is orbiting the Earth, you could actually calculate this by itself and pull out the square root of this number by itself, and then the only thing you'd ever have to do is multiply it by the square root of r cubed. If you really wanted to get efficient, because all of this, as long as you're orbiting the Earth, is going to stay the same. It's up to you. Your calculators can handle it. But I'm just saying, if you were doing this calculation by hand, every time, you would get this number by itself, and then you'd just be left with multiplying it by the square root of r cubed. Okay, so let's do the math. So somebody take, let me get rid of this so we have some more room. The square root of 4 pi squared, and then that radius is what, what do we get when you added it all together? 6.4937? Okay, now, let's look at order of magnitude again. Okay, let's just look at order of magnitude. So I got 10 to the 6th, and that's going to get cubed. So up on top, I've got 10 to the 18th. Okay? I got 10 to the negative 11th times 10 to the 24th. That gives me 10 to the 13th. Okay? Excuse me, 10 to the 11th. My bad, 10 to the 11th. So when I take 10 to the 18th and divide that by 10 to the 11th, I'm going to get the square root of 10 to the 7th, which is, again, conveniently, going to be something times 10 to the 3rd. So here's the kicker. And this is easy to remember. So when you calculate an orbital period in seconds, okay, this is going to be the key, in seconds, both the orbital period and the velocity are both going to be 10 to the 3rd. Okay, so it isn't like you have to remember one number for period and one number for velocity. Both your orbital periods and your velocities on your Earth orbit, it's the same thing with the moon, should be 10 to the 3rd. Okay? So if you do this calculation and you get like 10 to the 7th or 10 to the 8th seconds, train wreck, something's bad, okay? Or worse yet, you do this calculation and you get like 10 seconds. Think about this. You're going to orbit all the way around the Earth in like 10 seconds? No, okay? It's not going to happen. All right, so Lauren, or who has ever got the calculator out, give me the numbers. Take 4 pi squared times that cubed divided by big G times the mass of the Earth.
It's
5,200 and what?
It was 5,206, but to make it recent,
Beautiful. Now, Lauren, take this and divide it by 60 so we know how many minutes that is.
it's 86.8.
So, about 87 minutes, okay, right? So that's about an hour and a half. So that's typically about like how long it takes for the International Space Station to orbit. It's about an hour and a half depending upon the orbit. So here's the deal again. Play the what if game. So since this is r cubed, if you boost this thing into a higher orbit, you're going to have a bigger radius, which means you're going to take longer to go around. So, and that goes hand in hand with the velocity decreasing. So as you go into a higher and higher orbit, two things happen. The orbital period gets longer, and the velocity becomes slower. So one of the questions on your assignment is going to deal with a geosynchronous satellite. So what happens on a geosynchronous satellite, and we need these for navigation, is that, so imagine here's a satellite, right? And you want to park it right above Mays, Kansas. So what you want to do is you want to put that satellite in an orbit so that as Mays is moving around and spinning on its axis, that satellite is going to be directly above it. So since it takes the Earth 24 hours to spin on its axis, that's how long that satellite has to have as an orbital period. So if you're on a near-Earth orbit, okay, that's only going to take you like an hour and a half. So on satellites that are in near-Earth orbit, like the International Space Station is, okay, those are going around really fast. So those are going much faster than the Earth is spinning on its axis. So we're actually being lapped by near-Earth orbit satellites. But the geosynchronous ones it's like a parking lot that holds these geosynchronous satellites, and they stay above us all the time as they're going around. Okay. So here's the next big thing.
Josh needs back in, he got booted.
Oh, Lord. Thanks. Josh, are you back in? Okay, fantastic. All right. All right. So now, here are the last two big ideas. So we're going to go back up to this problem, and then get rid of all of this. Okay? So here's the last two things we need to do with this problem. We need to calculate the centripetal acceleration and the value g at this altitude. Okay? So here's the deal. So when you talk about that centripetal acceleration, I don't care how you do this. You could use 4 pi squared r over t squared, or you could use v squared over r. Okay? Either way, you're going to get the same answer. So this one's probably going to be a little bit easier, so let's just go with this one. So on that centripetal acceleration, what was the velocity? 7.87 times 10 to the third meters per second. Now, what did we end up as the radius? 6.4937 times 10 to the sixth meters. Okay, now, let's look at this. Order of magnitude. I've got 10 to the third squared, which is 10 to the sixth, I'm going to take 10 to the 6th, divide that by 10 to the 6th, which is going to give me like 10 to the 0. So I've got to figure that this answer isn't going to be very big, because I'm taking 10 to the 6th and dividing it by 10 to the 6th. Okay? Which means if I get it like 10 to the 3rd or something like that, I've done something wrong. So somebody take 7.87 times 10 to the 3rd, square that, divide that by that orbital radius of 6.4937 times 10 to the 6th. And let me know what you get. What'd you get?
I got 9.54 times 10 to the 10th.
Oh God, no. There's no way you got 10 to the 10th. There is no way on God's green earth. I can agree on the 9.54, but there's no way it's 10 to the 10th.
Yeah, I think I just read the exponential.
Did somebody else do it?
I got 9.46.
9.46?
Yeah.
That I can live with. Okay? Yeah, Lauren, figure out what you're doing. There's no way that would be that big. Okay, everybody cool with this? Now, we have one last calculation to do. Okay? One last calculation. And now we're going to try and figure out what little g is at this point. Okay? Not to be confused with big G. So, we got little g is going to equal big G, mass of the Earth divided by that radius, 6.4937 times 10 to the 6 meters squared. Okay? So, again, this is like 10 to the 12th. That's going to work out to be about 10 to the 12th. I shouldn't have any exponent at all left over on this deal. Or if I do have an exponent, it shouldn't be very big. So somebody plug in big G, mass of the Earth, 6.4937 times 10 to the 6 meters squared, and let me know what you get. There's no way you got 4.46. No way.
9.46.
9.46. That's what you should get. Oh! How cool is this? Look, my centripetal acceleration at that altitude is the exact same as my gravitational acceleration is. Coincidence? I think not. These two numbers have to be the same. Because look, when this thing is in orbit around the Earth, that centripetal force is what's being created by the gravitational field. So mathematically, here's what's going to happen. If you set that centripetal force equal to the gravitational force, okay? So here's where the magic happens. So that's going to be mass times my centripetal acceleration, okay? That's all it is. It's just mass times my centripetal acceleration, which is equal to big G, mass of the Earth, mass of the satellite, that's the mass of the satellite, divided by r squared. But we also said that that equals the weight, which is the mass of the satellite times G. So all three of these things are equal. your centripetal acceleration, mass times your centripetal acceleration, which is created by the gravitational force, which is also equal to the weight of the object, which is the mass of the satellite times g. So what happens is, oddly enough, the mass of the satellite drops out of all of these. So what you're left with over here is that centripetal acceleration is equal to your gravitational acceleration. So what that means is that if you could launch a satellite right at the surface of the Earth, okay, like right here, the only reason that we put things, quote, into space is so that we can get above our atmosphere. There's nothing magic about space other than it's outside our atmosphere. If we didn't have an atmosphere, we could literally put satellites at the same altitude that planes fly at, okay? And you could look up and you could go, oh, look, here comes a satellite. So we wouldn't have to put them into really far Earth, really high orbits. So if you could put something at an orbit right at the surface of the Earth, the centripetal acceleration it would experience as it falls would just be equal to 9.8 meters per second squared. So the reason that that value is a little bit less is because of the fact that we're further from the surface of the Earth. So as you go further and further and further from the surface of the Earth, your centripetal acceleration becomes less, your gravitational acceleration becomes less, because you're further from the center of the Earth and you don't have as much gravitational pull. So this is one of the main things that you need to understand, is that your centripetal acceleration is equal to your gravitational acceleration. Okay? That's one of the key things that you have to get. Okay. Now, that was exhausting. How much time do we have? 15 minutes. Okay, we're good. Okay. And make all this go away. So here's another type of problem that you have to be able to do without giving it any thought. Okay? So, what we have here, the newly discovered planet has to move with an orbital period of 20.5 hours and a radius of 3.68 times 10 to the 6 meters. What's the mass of the planet? So if you look at any data table, mass of the moon, mass of the Earth, mass of the sun, whatever it is, we don't have the capacity to stop these planets, put them on a scale, and go, oh, here's the mass of the moon. Oh, here's the mass of Jupiter. Okay, here's the mass of Saturn, whatever that is. We don't have that capacity. So what we have to do is we have to make indirect measurements of what's happening caused by that gravitational field, and then we can work backwards and figure out what that mass of that planet is. So, here's the story. So we've looked through a telescope, and we have figured out that we've made observations about this moon, so we know the orbital period of the moon, we know the radius of the moon, and we want to figure out the mass of the planet. So right away, you can go, oh, okay. If you go to that Swiss Army knife equation, so you have 4 pi squared, r cubed equals big G mass times t squared. So we know the radius, we've got that, and that's already in meters, so that's cool. We got the period, which is 20.5 hours. So this right away should throw up flags. You cannot leave this as hours. Okay? You cannot leave this as hours. You have to change that into seconds and to put that in here, or otherwise the units are a train wreck. You got the radius, so the only thing we don't know is the mass of the planet. So if we solve this, and we go 4 pi squared r cubed divided by big G t squared, then we can get the mass. So we're going to have 4 pi squared times that radius, which is Okay. So, again, here's what you're going to screw up. Mark my words on this one. You're going to forget to square this pi. Okay, that happens a lot. Be careful how you input this into your sequence on your calculator. You're going to forget to cube this number. I've seen that happen as well. But without doubt, the most common mistake is that either you forget to change this into seconds, or you do that and then you're so excited, it's like, oh, I actually put it into seconds. Cool, right? I'm excited. But then you forget to square it at the end. Okay? I've seen that happen as well, a lot. So, this calculation, again, pretty much just challenges your ability to do numbers on a calculator. Now, if you notice what I did, I always solve these equations first because, trust me people, it's a lot easier to solve this for an R or a T or whatever it is, just in terms of variables, and then put in the numbers, okay? Don't put all your numbers in here and then try and solve this thing. You can do it, but it is going to take you so long to do. It is going to be much more efficient if you can just solve these for variables first, and then the last step is you actually put in the numbers, okay? That's just something to think about, okay? So, what do you get as an answer? Everybody cool with that? Now, to give you some perspective, our moon has a mass of like 10 to the 22nd, okay? So that isn't that far off, all right? Seems reasonable. It's going to be small for a planet, but it isn't like we got, 5.42 times 10 to the 5th or something like that, okay? So that's a fairly reasonable answer, all right? So there's a problem like this on your assignment where you're going to solve this for the mass of, I think, Saturn, okay? And you're going to do something like this where you're given information about, I think it's Mimas, okay? And you're going to try and solve for the mass of Saturn. So this is how you're going to work that problem. Okay. Now, in the name of time, I am going to shut down the video camera for the YouTube, okay? But I am going to keep this one going. So give me a second, I got to move stuff, okay? Oh, Lord. Okay. We're moving, okay? Okay. All right. So one of the ideas espoused by Einstein is that space and time are like a fabric, okay? So this is just like a big stretchy piece of spandex. So you can actually model a lot of cool things with this. So one of the things you can do is like, you can talk about Newton's 3 laws of motion. So if I take this little marble and I roll it across here, okay, notice that it just travels in a straight line, okay? It doesn't curve, it just goes back and forth in a straight line, okay? because there's nothing around it to cause a disturbance. However, if I take a bigger mass and put it in there, notice that that curves space and time. So right now, all of you are curving space and time around you. Now, don't put that on your college application that says, what's your superpower? Oh, I curve space and time. Everybody does it, okay? It's just not you. But now look what happens. Now when I roll that marble by it, notice that it follows a curved path, okay? So, and if I could put that at just the right speed, notice that it would just pretty much go in orbit. Now, so everybody tends to focus on this, but you can actually demonstrate Newton's third law as well, that says for every force there is an equal and opposite force. So, look what happens when I roll this by. When I roll this by, this will move just a little bit. Not much, it'll move just a little bit. So when that goes by, this gets a little bit of a wobble, okay? It just gets a little bit of a wobble. So that's an example of Newton's third law. So when you get this action-reaction, so when that goes by, this is also creating a small curvature in space, which causes a force on the larger ball to move, but not near as much as it does for the little one. Now, let's say that we want to go to the moon, and this is going to be one of the problems, okay? So imagine here's the Earth, much deeper gravitational well, and here's the moon. So one of the things, and I'll go through the math really quickly after I get done, is what's called the Lagrange point, okay? So if you want to go to the moon, you're going to launch, you're going to orbit around the Earth a couple of times, you're going to fire the engines, and then you're going to go towards the moon, and then you're going to get caught in that gravitational field, you're going to orbit around the moon, you're going to fire your engines, and then you're going to come back towards the Earth. So that's the short version of what's going to happen. So, but here's what happens. If you're not going fast enough when you leave the Earth, what happens is that you're just going to get pulled back into this gravitational well. What can also happen is when you're going towards the moon, if you're going too fast, then you're going to overshoot the moon, and then you're not going to get caught in its gravitational field, and then you're going to get slingshotted back like this on a big figure 8, okay? Which isn't going to end well. Hold on. Let me try it one more time. Come on. There we go. That's what I'm looking for, okay? So, if you can also model this in terms of like forces. So if this is the command module, and if I put it right here in the middle, and I let go of it, it's going to roll back towards the Earth. If I put it too close to the moon, then it's going to roll towards the moon. So one of the things you're going to calculate is what's known as the Lagrange point. The Lagrange point is the point where this thing has an equal pull back towards the Earth and towards the moon. So on the Lagrange point, basically what you're trying to find is the middle of these two gravitational wells. So the moon has a lot smaller mass. This has a much bigger mass. So what happens is that if I put this kind of like right there, then it's going to stay. So what's happening schematically is that this is the middle of these two gravitational wells. Mathematically, what's happening is the gravitational force pulling towards the Earth is equal to the gravitational pull going towards the moon. So what that means is that if you could park this satellite right here, and you could stop it, you could put it right there, as the moon orbits the Earth, this spaceship would stay exactly right there and move with it, because it would have an equal pull between these two. That's going to be one of the questions on your assignment. Now, the other thing that you can kind of do is model like a binary star. So if I have two equal gravitational wells, and this kind of gets random, so we'll do this, we'll roll this around, okay? And what you'll see is that you really get these kind of weird patterns that go onto this deal, because now you have two gravitational wells. Hold on. We got to end on a good note. Hold on, that wasn't very good. Ah, that was even worse. One more. Ah, that wasn't bad. Okay, so when you get two binary stars and you have two gravitational wells, then you get some really weird action going on. Oh, that was a good one. We finished it up on a good note. Okay, so we got that. Now I'm going to move everything back up there to the front. Yes, here's one last look, one look around the room. Everybody can see where they sat. Okay, there you go. Room's still here. Oh. Dear Lord, I had some papers and I just, okay. Fine. All right, so one of the questions is going to be this question of the Lagrange points. And I don't remember which question it is, but here it's going to be the Lagrange point question. It's the biggest, longest question on there. It's going to have the diagrams with the moons. So here's the deal. So what you're going to do, and I'm going to show you two different ways to work this. And we're going to go a little bit past the time, but stay with me here. It's going to be worth it. So, yep. You can't what? Oh, you're so demanding, Lauren. Seriously. My God, child. How's that? You can see it now? God. Next thing you know, you're okay. Okay. So here's the Earth, here's the Moon, here's the Lunar Command Module, okay? So we're going to try and find the single point where the gravitational force pulling back this way is equal to the gravitational force pulling this way, okay? So what we're going to do is that we're going to set this as this force between the Earth and the Lunar Command Module is going to equal the force between the Moon and the Lunar Command Module, okay? We're going to set these two values equal to each other, right? So here's the deal. And do not write all this down. I'll tell you when you really need to start writing stuff down on this problem. So this is going to be big G, mass of the Earth, mass of the Lunar Command Module, and I'm going to let this distance be x, okay? This is just some distance. I don't know what that distance is. I'm just going to let this be a distance x, okay? But that's going to be x squared. Now, that's going to equal big G, mass of the Moon, times the mass of the Lunar Command Module. Now, here's the kicker, okay? I need this distance, but the total distance from the Moon to the Earth is 3.844 times 10 to the 8th meters. I swear, if you ever had a trivia game of like, hey, give us random physical numbers, I would win hands down. What's the distance from the Earth to the Moon? 3.844 times 10 to the 8th meters. Okay. What's the mass of the Moon? 7.22 times 10 to the 22nd kilogram. Okay. So anyway, so here's this total distance. So whatever is going to be left is that total distance minus x. Okay? So this is going to be 3.844 times 10 to the 8th minus x squared. Okay? Now, because these two things are equal, notice that the mass of the lunar command module is going to drop out. I don't need that number because it's going to drop out. That's why I didn't give you that mass. Big G is on both sides of the equations. I don't need that either. So I'm going to lose big G. I'm going to lose the mass of the lunar command module. Now, what I'm going to do is I'm going to cross multiply at this point because I hate fractions. Okay? So this is what you really need to write down. So we're going to have the mass of the Earth times 3.844 times 10 to the 8th minus x quantity squared is going to equal the mass of the Moon times x squared. Okay? Now, what I'm going to do is I'm going to take the mass of the Earth, I'm going to move, and I'm going to divide it by the mass of the Moon. Okay, so I'm going to move this over here. Okay? So I'm going to divide by the mass of the Moon. Now, trust me on this one. I'm going to give you this number just to save you some time. If you take the mass of the Earth and divide it by the mass of the Moon, you get 81.35. Okay. Now, at this point, you have a decision to make. You can go hardcore quadratic. You can expand this, okay, as a quadratic. Okay, this is an option. You could expand this as a quadratic, get this squared plus x squared, that times x times 2, just like on that FOIL method. You could expand this. Then you could distribute 81.35 over all of that. Then you could move this x squared over here. And then you could use the quadratic of negative b plus or minus b squared minus 4, or b squared minus 4ac all over 2a. You could do, if you want the most complex quadratic equation in the world, you could do this. Okay? But there's another way. Yeah, I'm just saying that's an option. Here's your other option. I'm going to take the square root of both sides of this thing. Okay? Now, because that's plus or minus, the square root of 81.35, trust me on this one, is plus or minus 9.02 times 3.844 times 10 to the 8th minus x is going to equal x. So here's your other option. This is how you're going to get your two possible roots. Take a positive 9.02, multiply that across, okay? So you're going to get this times this minus 9.02x equals x. Get your x's on one side, solve for x. That's how you're going to get one root. The other one is that you take negative 9.02, you distribute that, you still have that x over there, combine your x terms, and that's how you're going to get your two possible roots. So here's the deal. When you do this, if you do it right, you're going to have two Lagrange points. Here's the Earth, here's the Moon. One Lagrange point puts you between the Earth and the Moon. The other Lagrange point puts you out here outside the radius of the Moon. So when you get those two Lagrange points, one's going to be here, the other one's going to be there. So that's how you can check that you got those right. So if all goes well on those Lagrange point questions, both of your answers should be something times 10 to the 8th. Okay? Both should be 10 to the 8th. Okay, I've kept you long enough. So again, this assignment is going to be due on Thursday. My plan for tomorrow is to work some more of these problems because there are some real specific ones that I want to work, especially out of the textbook. So I would give this a good college try so that when we come in tomorrow, you can say, hey, Burkamp, we know these are the ones that we really want you to work. Okay? So I'm out. Good luck. And I'm also going to send out the reviews for the test. They're the same ones that I give my honors kids. And I'll tell you which ones not to worry about, because there's one particular problem that you guys won't have to worry about, but I'll tell you that. So I'm going to send those out as PDF files today as well. All right. stay safe, stay away from people, and I will see you all tomorrow.
Hey, Bergkamp, I got another message from Tanner here.
What's that?
He said next Tuesday on Africa Day, he's gonna make ranch eggs with you.
Okay,
Make ranch eggs.
fantastic. All right, sounds like a plan. Tell him I said hi.
Alright, I'll tell him.
All right.